So this is section 1.1. 1.1 talks about real numbers and the real number line. In algebra, we are generally talking about real numbers, with the exception, on occasion, we will discuss another concept called imaginary numbers, but that's a very specific case. Most of the time, we will be talking about real numbers. So in this slide, what you see are the subsets of real numbers. Real numbers basically include all those numbers that we think of when we think of the real number line, which basically means all rational numbers and irrational numbers. Rational numbers include whole numbers, and you can see the example of what whole numbers means, and also integers, which adds the negative values to that whole number set. Rational numbers, by definition, are any number, or a rational number is any number that can be expressed as a fraction of integers, like 3/4 or 1/3, or -4 can be expressed as -4/1. Those are all rational numbers. Irrational numbers cannot be expressed as a fraction of integers. They are non-repeating, non-terminating decimals. Values like √2 and pi are examples of irrational numbers. On this slide, there are three definitions. The definition of the origin of a number line, and you can see the origin is located by the real number 0 on the number line. The graph of a number, so if I want to graph the number 1 on a number line, then I put a point at that location. And the coordinate of that point is actually the number that corresponds to the graph. So the coordinate of this point, the coordinate of this graph is 1. So here you see an example of graphing the real numbers -1.8, the square root of 3, and then 5/2. So the inequality symbols can be used to order real numbers on the number line. So for example, -4 would be less than 1, and -5 would be greater than -7, or I could say -7 is less than -5, like that. But these inequality symbols can be used to order the real numbers on the number line. Smaller values are always to the left on the real number line. On this slide, you see properties of real numbers. So on the left-hand column is the list of the properties: closure, commutative, associative, identity, inverse, and distributive. A, B, and C in these examples all refer to real numbers. So for example, for closure, the property simply says, well, for addition, if I add two real numbers, the result is a real number. If I multiply two real numbers, the result is a real number. That's the closure property for both operations, addition and multiplication. The commutative property simply says that if I'm adding two numbers, the order in which I add those numbers will not change the result. The same concept applies to multiplication. The order in which I multiply two numbers will not change the result. The associative property means that if I'm adding three or more numbers, the manner in which I group those numbers will not change the result. So for example, if I add A and B together, get that result, and then add C, that final result will be the same as if I were to add B and C together first and then add A to that value. The manner in which I group the numbers when I have three or more numbers won't change the final result. Same concept would apply to multiplication. The identity property for addition, adding 0 to any real number, the result is the original real number. Or multiplying any real number by the value of 1, the result is the real number. The inverse property for addition, adding a number and its opposite, the result is 0. For multiplication, the inverse property means multiplying a real number times its reciprocal, the result is 1. And you can see the caveat that A cannot be equal to 0 in this definition because 1 over A would be undefined. Finally, the distributive property. I can see on the left-hand side there's a factored form of this product. On the right-hand side, if I actually distribute, if I multiply the A times the B, multiply the A times the C, and add those two quantities together, that those are equivalent expressions. One is in distributed form, one is in factored form. And all these properties apply to all real numbers, rational numbers, irrational numbers, all real numbers. So if I'm identifying the property that's shown, well, here I can see what's being shown is that if I add two numbers, the order in which I add those numbers does not change the result. That's an example of the commutative property of addition. If I multiply a number times its reciprocal in part B, 5 times 1/5, the fact that the product of those two values is 1, that's the inverse property of multiplication. So up the top of the slide, the opposite or additive inverse. So another way of saying the opposite of a real number is the additive inverse of a real number. So the way I indicate the opposite of a real number, for example, the real number A would be the opposite of A, the negative sign here, the opposite of A. The reciprocal or multiplicative inverse, again, those are synonyms, of any non-zero number. I can't divide by 0, but the multiplicative inverse or the reciprocal of A is 1 over A. I can define subtraction as adding the opposite. So in other words, one way to define A minus B is to say, well, that's equivalent to A plus the opposite of B. I can define multiplication in terms of division. I can define division in terms of multiplication. Dividing A divided by B, I can redefine that as A times the reciprocal of B. Again, B cannot be equal to 0. So in these examples, the difference of -3 and -15 is, the key word here is difference. This means, what's the value if I were to say -3 minus -15? -3 minus -15, 12. The quotient of -18 and 1/6. What's the quotient? In other words, what's the value if I were to say -18 divided by 1/6? -18 divided by 1/6, -108. Finally, you can use unit analysis. This is a science application. Frequently applies to word problems. You can check to see that you've set up your problem correctly by using unit analysis to make sure that when you multiply or divide, that in your final answer the units make sense to the problem that you're solving. So for example, in part A, well, if I'm adding two values and they're both in the same units, the final answer is in the same units. So 685 plus 225, 910, and the units are in feet. In the next example, if I'm multiplying hours times kilometers per hour, hours in the numerator will cancel with hours in the denominator, and the result will be in kilometers. So the final answer here, 2.25 times 60, 135 kilometers. And finally, in the third example, when I multiply, seconds in the denominator cancels with seconds in the numerator. Feet in the numerator cancels with feet in the denominator. And my final answer will be in terms of miles per hour. So when I check my final answer, that final answer, 45 miles per hour. 66 times 3600 divided by 5280 is 45, and the units are miles per hour.